Makes the middle board unique and distinct from the outer two?
It should be an addition reaction where you do the bromine.
It has
attach.
2 double bonds instead of
No. It is 2 double bonds to begin with. If we look to the outer sides, we don't have 2 double bonds. Really?
You have 2 pi bonds.
We have 2 pi bonds over here. Why is the middle board distinctly different from the one on the outside? Why is diene matter versus alkyne?
That's the way it is.
It's just how it is.
Which pi bond should you react? Well, so the middle board, you can't tell me, I don't know. You circled one. You think you should react one of those pi bonds over the other.
This one would create a more stable intermediate.
Okay, so when we look at that middle board, there's a difference between those pi bonds. When we look at our far, my left, I guess for those at home, the black reaction, there's only 1 pi bond. There's nothing to choose from. We don't have to worry about it. Okay, our orange reaction had 2 pi bonds. They're different from each other. So we have to think a little bit more carefully about that. We're going to come back to those as potential products in a second. With our alkyne, we do still have 2 pi bonds. Why does it not introduce the same issue as our black one? Or sorry, our middle one. So our orange. Why orange versus blue? They both have 2 pi bonds. Why is the orange one particularly more challenging?
You have to decide which one is the better one to react.
What are you saying about the blue one? Is there a difference between those pi bonds?
No.
No. That's why it didn't matter for the blue one. For the orange one, it does potentially matter. So for our outer 2 or our black and blue reactions, we said there were 2 possible products. Are there 2 possible products for the orange one? Yeah is a little bit of a true statement, but it's also massively an understatement. There's 4. Depending on which pi bond you react, and now the regiochemistry, where you're placing the hydrogen. So what we're looking at in each of these scenarios is regiochemistry. Where do I place the hydrogen? That's a regiochemical analysis. Okay, we're talking about the hydrogen because the hydrogen is the acid. It's the strongest active thing. We want to react that with the pi bond. Okay. How do we decide between those? Well, with blue and black, it gets a little bit easier because what did you do? Primary versus secondary. Okay, in the case of what was primary, actually both of them are technically primary and secondary. Okay, in the orange one, how do we decide which one is best? Can you just use primary versus secondary? No, why not? We have to take into account the other pi bond because what could that other pi bond do? Resonance. You mean there's a potential for some other chemistry happening there? Yeah, we have to watch out for that chemistry because that could get in the way. Okay. As soon as we have a pi bond, we need to be thinking about the potential for resonance and another nasty word, which we'll see in a little bit, rearrangements. So when we look at that orange one, the initial pi bond that was shown to be reacted was a primary carbocation or generated a primary carbocation. That is not stable. That should not be forming. If we compare it to its other possibility, the other possibility with that same pi bond would be a secondary carbocation. Is it only a secondary carbocation? With resonance. Okay, so in my shorthand, I call that secondary plus. If we move to the other pi bond, we could form a tertiary. Okay, or secondary plus. When we go through to try and predict our reactions, we need to be thinking about all of those potential outcomes. So when you get systems with asymmetry or different pi bonds, you need to be thinking about all of those other outcomes. That becomes challenging, which means you need to draw those other outcomes so that you get used to recognizing those patterns. Does that make sense? When we look at those 3, we eliminated the primary off the list. What about the other 2? We have secondary plus resonance or tertiary. Which is more stable? Secondary with resonance is more stable, which means the initial assessment where you guys circled the tertiary becomes a little bit challenging because
Results that weren't shown.
our secondary plus resonance is probably going to win out, particularly because if we look at this one, it's secondary plus resonance, and what does that resonance result in? A tertiary. Okay. So differentiating our electrophil or our addition reactions, we have to be aware of that secondary issue of resonance. Is that something that's easy to miss? Yes, absolutely. It's something that I miss. Okay? So we have to pay attention for those extra pieces and watch out for that because it will bite us. Kind of, sort of? Okay, cool. Rotate boards. Go ahead and start the recording again while I try and draw it out. So as we kind of navigate all these things, that middle one, it's okay. Pull this one out. Where do you guys have questions? It is a lot, so that may mean it's difficult to ask a question. Nothing? Bueller? It took me a little too long to hear what that was. Adolfo is here even when he's not. We did walk through technically the blue one, but we didn't actually walk through the orange one. So the hive mind group, because I didn't get the whole group to come back to that one. Anyone want to kind of summarize what was going on with that? Don't all at once, might scare people. It was a joke. This is going to be hard. I'm going to try this. See how well this works. It's not working very well. Already tripping on myself. Where we ended on that orange one is which product to form. Right? And if we kind of remember, I'm just going to draw a base, pick up that hydrogen. Within that, the first group through picked the bottom structure, so we'll type that in green, and their explanation for the bottom structure was tertiary plus being more stable. Right? And then the question that was asked to everybody, or the next group that went through, I'm still shocked you didn't just ask Abraham, like, what are you talking about? What? Can be an easy fix. The next group was told, make the top product the better one. Okay, so come up with an explanation for why the top one should be more appropriate. And there was a little bit of stuttering on it, but eventually what they came to was that the pi bond was more substituted. Is that good enough? Writing it like that? Ish. Okay. For the record, I just cheated on this mechanism. Actually, no, I didn't. Not quite. So why? So which one is the correct explanation?
Could it be both?
Yeah. Right. Which is a bit obnoxious and misleading, but when we look at that orange reaction, both of those products are valid products. Right? And deciding which one is the major product requires more information to be able to finagle the system. Okay? Because what we're starting to address within that system is the concept of kinetics versus thermodynamics. Keto. That concept is going to show up again and again and again in second semester, and it's something that even in biochem our systems go through and control. Biochemical reactions will shift things kinetically or thermodynamically depending on what they're trying to navigate through. Okay? Some of that is limited because when we think about thermodynamics, we think about what? Heat. Okay? Why in a biological system is it not going to heat things up a whole bunch?
You don't want to catch on fire.
Because then you kill the biological system. Biological systems usually have a relative homeostasis about temperature where they can't change the temperature too much. So what they would have to go through and change is the energetics of those individual reactions, okay, through local changes. Those local changes are driven by our proteins. Those proteins change the local energetics so that your thermodynamic and kinetics can kind of dominate in that system. Do you have to worry about which product you get? No, because what is the biological system designed to do? Get only one. Okay, so in a biochemistry class, you don't have to worry necessarily about which one do I get, because the biological system forces one. And when you're asked the question, why does it do that? You go, because it wanted to make that thing. Why else would it do it? Okay, OChem, not very refined. Okay, bottom line, what OChem does is we take a bunch of chemicals, we put them into a black box, we shake it around a whole bunch, and then we pull stuff out and hope it worked. Okay, that's what organic chemistry does. Okay, and it's a pretty piss-poor system, except that we can take advantage of varying energetics and bond natures to ensure that when we put those pieces into that black box, they're in there in an appropriate energy and dynamics to allow the reaction to proceed in a ratio that's good enough for what we're trying to go through and do. Right? So while it seems very inelegant, when we do it, it flipping works. That's kind of cool. Okay? This is also why you get lots of active research in organic chemistry of trying to create different, effectively, proteins or enzymes to complete those reactions in a much more controlled fashion so that we can maximize those yields. Okay? Or we just straight up cheat and we make the biological system do it for us, and then we kill it, isolate it, and then use that as an enzyme over and over and over again. Okay? So, thermodynamic versus kinetic. When we're looking at those two products, how do we evaluate this? Okay? The first group, again, said that this bottom system was the major product. Their explanation was tertiary plus. Okay? That's the notation that we've been using for resonance. Tertiary plus resonance is more stable. If we look at the product, though, there is no resonance, particularly resonance that's going to generate a tertiary structure. So they aren't referencing the product. What are they referencing? The intermediate. And when we go back and look at the intermediate, absolutely. The intermediate there is more stable. And if the intermediate is more stable, that would most likely mean we get that product faster because it's there. Okay? And so what you're addressing is a kinetic aspect of the reaction. How fast does the chemical reaction happen? Okay? If we look to the top structure, the explanation for why that is more likely is saying the pi bond is more stable. Well, now they aren't referencing the intermediate, they're referencing the raw energy of the products. And when we go through and look at the products that were formed there, those two possible products, blue's probably a bad color, but we'll call it blue versus green here. Okay? The pi bond is the highest energy thing. Okay? Which pi bond is more stable? The top one, because it is tri-substituted versus di-substituted. That tri-substitution means that product is lower in energy than the other product. What you're talking about now is the actual isolated material, your product. And when we're looking at reactants to products and their relative energies, what we're talking about now is thermodynamics. Okay? So how do we decide which product we get? A lot of that's going to come down to the reaction conditions that drive this. Okay? Or that, I would argue what we should shift to, would be an energy diagram, which means I got to erase the bottom of reaction. Am I okay to erase the bottom of reaction?
Sure.
Okay. I can undo the erasing this. So if you're already, I could undo it. Okay. So we'll call it blue and green. If we look at the overall reaction here, we had one step. We had resonance, which really isn't a step. And then we had two steps, which means if I looked at the energy diagram, what would I expect to see? Two humps. Okay? So I would start with my reactance. The reactance would then become an intermediate. The intermediate was our resonance structures. Should those be higher or lower in energy than my reactants? Higher. So I should show my intermediate up here. Okay? Then I've got my products. Should the products be lower in energy or higher in energy than my intermediate? Lower because? Not charged. Awesome. Should it be higher or lower in energy than the reactant? Why lower still? Why is it more stable?
Less pi bonds.
We start with 2 pi bonds versus 1 pi bonds. Pi bonds are higher in energy. This sets up a relative system, and I don't care about the exact specifics, but as long as we're kind of touching on those points, we're okay. Okay? This diagram is going to introduce an issue. Okay? The big issue being, I don't have one product, I have 2 products. Okay? So I need to be a little bit clearer with my products here. Okay, I'm going to pick green. It's kind of arbitrary, so don't stress about that. Okay, I'm going to draw that product as green. So if I were to go through and now complete my energy diagram, whoa, that kind of missed. Try that again. Maybe I can get a little better. Close enough. Okay, and I now have an energy diagram representing the formation of the green product. Okay, but again, I've got 2 products, which means what do I have to do? Well, I need to make sure my energy diagram accounts for the blue product. It can't go on the green curve because it's a different product. Okay? Is the blue product more stable or less stable than the reactant? More stable because? Less pi bonds, the exact same reason. Is it more stable or less stable than the intermediate? More stable because? Not charged. So my product 2 needs to appear somewhere in that range. Okay? I need to know where it is relative to the green product. And I would do that based off the analysis that we went through and did already. You're now comparing the energy of the products with that. And we said the pi bond being more substituted. If it is more substituted, what does that mean to its energy? It's lower in energy than the other one, which means I should be showing the blue one down here. Kind of, sort of? Okay. Now we have to fill it out. Definitely the same reactant. What about the intermediate? Is the intermediate the same for both? And this becomes a really tricky statement, and one that I've bollocksed in the videos. Okay? Because I treat these, where did they go? Treat our resonance structures as different intermediates. Why is that bad?
Because the resonance structures, they're going to have similar, there's the same energies essentially.
Which structure is correct? They both are. Resonance is the same structure. I can't call it something different. Which means when I go my energy diagram, my intermediate's identical for both as well. Okay? But what that resonance is going to do is change the activation barrier to form the product. Okay? If that tertiary is more stable, that means I'm going to hit a lower space than I will for the other one. Which means my blue curve is going to look, I know it's not super dramatic, a little bit different. Why does this become important to me? Well, what's happening here is I get the blue activation barrier and the green activation barrier. That blue activation barrier is smaller than the green, which means it goes faster. And if it goes faster, I could say that that product is the kinetic product. What did we call the blue product? Or sorry. Whoops, I drew it for the wrong one. Fucking idiot. Okay, well, we're already drawn, so let's talk through this. Okay, in the system is drawn, so officially it's wrong, but we'll come back to that. I almost always draw it the other way. Okay. Which product would be favored? Which one happens faster? Blue or green? Blue, which means that's a kinetic product. Which one is thermodynamically favored? Blue. So all paths for this energy diagram say we get blue product. Okay? Is this energy diagram accurate to what was shown up here? No, because I goofed the part. I said the tertiary carbocation is more stable. The tertiary belonged to the green path, which means the blue path is higher in energy, and I'll just super accent it. Why does that become important to me? Same kind of questions come out of this. Which path happens faster? Green. Why? Less activation energy to clear that hump. So the blue will happen slower. So if I mix these reagents, what product do I expect? That was the initial phrasing of the question, and that's a bit misleading. You might say, well, the green, because it happens first. Okay? Well, there's other things that we could do to change that kind of dynamic. Okay? If we make the reaction incredibly cold, what happens? Do I ever get enough energy to clear the activation barrier? No, which means the only reaction that progresses forwards is the one with the smallest activation barrier, which means I get the green one. What happens if I flip it and now heat it up? Let's say now I'll make it wicked hot. Do I have enough energy to clear the activation barrier? Yes. Which product forms first? The green. It's still the green. But Mike, what about the other product? Okay? The kinetic product will always form first. Okay? When we add heat, we are adding heat that we can potentially clear the second activation barrier, our blue one. That's absolutely true. Okay? So by adding heat, we can increase the amount of thermodynamic product, okay, by clearing that activation barrier. But the adding of heat isn't worried about that activation barrier. It's worried about that activation barrier. That activation barrier is for the reverse reaction. And when I'm hot, I will still form the green product first. But once I'm hot, I can reverse that reaction. If I'm hot, I can still clear the blue activation energy. And now I move down to that bottom one. What becomes the challenge now? To reverse the blue one, how much energy do I need? A lot more. So the blue one is now referenced as irreversible, whereas the green one is reversible with heat. So when we talk about the addition of heat, we aren't talking about the activation energy for the forward reaction. We're talking about the activation energy for the reverse reaction, okay, which is challenging. That requires an understanding of equilibrium, which is why you take Chem 152 before you get to this class. Okay? And theoretically in Chem 152, what did they teach you? This diagram. Okay? And if you go back and look at all the pieces that you studied, that is what they taught you. They just taught you the numbers of how to get each of those data points. Okay? And it is so easy to get lost in the numbers that we ignore the overarching process behind it. Once we have that overarching process, we can now apply that qualitatively to organic chemistry really, really, really nicely. Kind of fun. Or crappy at the same time. Right? For OChem 1, how big of a deal is this? 1, 2 questions on the final. Okay? So is it part of it? Yeah. Where it's going to be part of it is in the addition reactions. Okay? Which takes us kind of to our next level. If we consider what you have to do for your final, okay, the highest score, I think we said, was 60, right? Okay. You could miss 10 questions. This most recent content is probably 20 questions. Okay? So you could brush up on it a little bit to try and get half of those questions right, and then perfect everything else. You would achieve exactly what you need to advance. Okay? Which means you don't need to master this newest content. What you need to master is everything else. And the more that everything else is mastered, the better this content becomes, because everything we've talked about on all of these reactions in these boards has already been addressed. It's now just getting applied to a new scenario. Okay? So if you can master the old stuff and forget or ignore the new stuff, that's a pretty awesome score. Is it good enough? I don't know. Okay? But that's partly what you need to decide when going in and studying for this content. Okay? In that process of studying for the content, I would recommend you use the ACS study guide. Okay? That is something that was in the required elements of things that you should have purchased this semester. If you have not purchased it yet, it's probably not worth purchasing because the delivery time is going to be so long. Or you go to the bookstore and hope the bookstore still has copies. You'll pay double the price. Right? The convenience fee of going to the bookstore. Or penalty for not buying it earlier. Okay? Or you go to the tutoring center. The tutoring center has the most recent one, and it has 2 older versions. The older versions are pretty much identical to the new one, except the new one is organized better. Right? And so it has gone through and taken all the content that they think is first semester and put them into little chapters. So you get 7 chapters, 8 chapters, I don't know how many it is. Okay? And so what you can do to decide how well prepared you are is answer questions in those chapters. That's still a lot of questions. Pick 5 questions from each chapter. See how you do. If you're scoring 4s or 5s in that section, you probably don't need to review it. You're doing pretty well. If you're scoring 2 to 3 questions right, that's something you should review. There's a potential weakness there that you should master and ensure that you're locked on. If you're getting no questions or 1 question right, you should probably just straight up ignore that section. Right? Because that's a lot of work you now need to do to get yourself up to a higher level. Does that make sense? That creates a baseline. Within that baseline, you also have to be careful. Everybody says, oh, I want more time on the exams. Your semester exams have been designed to match the time per question on the final. Okay? Which means you're not getting more time. Okay? You get 110 minutes, but it's 70 questions. Okay? So when you do those 5 questions, 7.5 minutes. I may have done that math wrong. But time yourself for 7.5 minutes to answer those 5 questions, because that's all you get. Okay? If you're doing it in 20 minutes, that's not helpful. Okay? That'll give you the baseline. You can now go back and start doing the reviews within those. It gives you lots of practice questions. You can continue those. Once you know where you have weaknesses, you can potentially come back, look at practice exams or the actual semester exams. Make sense? With that, sorry, no questions today.